Hello, my name is Leonardo Santos and I'm an electrical engineering student at the Federal University of Minas Gerais in Brazil. This summer, I spent time working with Brady Moon and Professor Sebastian Scherer on multi-object tracking in the Air Lab here at Carnegie Mellon University, and I would like to tell you a little bit about my project. First, I want to invite you to think, why should we care about multi-object tracking? The first scenario you can think of is that some people just escaped from a shipwreck and they're now on boats wandering on the sea, and you need a drone to find and track them to assist rescue teams. You can also think about wildlife monitoring, where you want drones to track the behavior of animals for conservation purposes. And lastly, you can also think you're a farmer and you want some systems to monitor your lands. All these applications have one thing in common. We want to estimate the states, which can be the positions, of an unknown number of targets from noisy observations. But we can also go a little bit further, which is the case we consider in this paper. Here, we want to estimate labeled states, which means that each object must be uniquely identified from unlabeled observations, which means that when we get an observation, we don't know to which target it corresponds to. And we also assume we have limited field of view, which means that the drone must cover an area that's much larger than the area it can see at each time step. And for that, we propose the following framework. First, the drone estimates 2D positions of objects by projecting the camera image on the ground after running an object detection algorithm. And then, we estimate the unlabeled initial states of these observations using a 2D common filter. And then the output of the common filter is used as input to the Labeled Multi Bernoulli Filter, which takes care of the global label assignments and multi-object estimation. And for the Labeled Multi Bernoulli, we propose a dynamic birth model to generalize it to scenarios with limited field of view. Now, diving into the LMB, the first step is a prediction in which each object state is propagated using the object's motion model, and potential new objects are added using the dynamic birth. Second step is a grouping step in which the predicted object states and observations are separated into independent groups so we can perform the update into each group separately. Lastly, we perform the update in which the observations are combined with the predicted states to get more accurate estimations. In the case of the LMB, because of data association uncertainty, multiple hypotheses are propagated and then merged together using a weighted sum, in which the weights are the probability of the hypothesis corresponding to the ground truth. And with that, we get the posterior, and we've closed the loop, feeding the posterior as a prior to the prediction in the next time step, and the algorithm runs recursively. Our dynamic birth model intuitively measures the overlap between the measurement distribution and the target state distribution. What we do is we convolve both functions and construct a likelihood in which the higher the value, the higher is the likelihood of this measurement corresponding to this specific target. And with that, we get the following behavior. When there is more uncertainty about the target position, we get a higher association likelihood because there is more overlap, even if the measurement is in the same position. Next, we show the results we obtained and compare a baseline approach based on particle filters. In this video, you can see a simulation of an UAV tracking 20 ships, where of course the number of ships is unknown to the UAV, and each ship has a label associated to it when the UAV first detects it. This video is accelerated 8 times. First, we show a qualitative result of a typical run, and on the left, we see the trajectories estimated by the baseline approach, where the colored circles shows the estimated trajectories, and the radius of the circles are proportional to the variance in each time step. Each ID is represented by a different color. The green crosses represents where the UAV first detected the ships, and the ground truth trajectories are shown in black. On the right, we see the trajectories estimated by the proposed approach. Here we show a quantitative result where we compare our approach to the baseline and show that it successfully beats the baseline according to the optimal subpartner assignment distance. And with that, I'd like to thank you that watched this video to the end, Rachel Bursin and John, and all the race organizers for making this possible. And of course, Brady and Professor Sebastian for all the mentorship during the project.